Good morning. We're actually going to cover 2 lessons in one today to make sure that we can fit everything in as we need to before the exam this coming Friday. So what you see behind me is both lesson 2.5 and 2.6 moving forward. Lesson 2.5 focuses on earthquakes and 2.6 focuses on volcanoes. Now the reason that I put these both together is because they have similar causes and sources within the earth. So regardless, if we start with the earth here, we know that we're going to have seismic waves of some sort that happen and release energy into the earth. We're also going to have the convection caused by the inner core within the mantle having hot magma shift up and cool magma shift down. Because of that, we saw the 3 types of plate boundaries, so the convergent, the divergent, and the transforming. Because of these 3 things, we can see a shift and movement in the Earth's crust. And these 3 things are also what lead to both volcanoes and earthquakes. Let's start with earthquakes. When we have these waves moving through the Earth's crust, they can come in 3 different types. Now these are called seismic waves. And the 3 types are P, S, and L waves. The P waves are going to move the fastest. And those P waves are going to only go side to side. So they're only going to go side to side as they go through the planet. And they can go through solids specifically. They're the first to arrive if we're using a seismograph or something to measure seismic activity. So they're going to be the first ones. They're going to hit that reader and send a spike or signal on our chart. The second are going to be the S waves. They move at a medium speed, but are also a little less dangerous because they move up and down and up and down. What we notice here is that they only move through liquids. But there's one more type of wave that we have to talk about because they're called L waves. They move in every which way direction, which means that they can cause the most damage as they can move through solids and liquids and have the most energy they can release. So P is for fast, S is for medium, L is for dangerous. Sure. Now, in order to understand how this energy is released, there's another theory that we need to talk about. It's called the elastic rebound theory. And to truly understand that, we need to understand that all rocks are going to start in one way. And what the elastic rebound theory states is that they will bend, and then break. After they break, they release energy. But the 2 pieces that come because of it look just like those that started, except smaller. So you're going from here, bend, energy release. The 2 pieces look as if they did when they started, just smaller. And that's what we have pictured here. So we have our rock, the bend, the break, and the finish with 2 smaller pieces. Now looking at the same release of energy, we can see that magma, which is molten rock inside the atmosphere, can be released from these boundaries. So when they converge, they can cross and open a hole in the atmosphere, releasing magma, which will turn into lava. They can pull apart, diverge, and have that magma come up in a ridge, or they can transform, cause a crack in the crust, and then escape in that way. When we look at volcanoes, we see that when magma is present, it has a certain viscosity. And what viscosity is the thickness of a liquid or a fluid. And so when we look at water, water is not very viscous. It's thin. If you throw it somewhere, it's going to go and spread and splash out. But something like honey or syrup, if you throw that, it's more likely to stick. So honey or syrup is more viscous, more thick than is water. And that's important because when we look at the dangers associated with volcanic eruptions, we see that this magma underground has a specific set of gases that are trapped in it. So we have steam, carbon dioxide, sulfur dioxide, sulfuric acid, and hydrochloric acid. Those are all gases that are trapped within this magma. And the thicker the magma is, the tighter the gas is held as well. The more energy it's going to take to pull apart that magma for the gas to be released. So it's like trying to get syrup off something compared to water. Syrup, you're going to have to scrub, pull, it sticks more. Water will just come right up. So if we have water or less viscous magma erupting, the gas gets out easier, so it doesn't have as much built up energy. However, when we have more viscous, syrupy magma, the gas takes much more energy for it to escape, and it erupts much more violently. So we see that there's a lot of different characteristics that come into play. Three important ideas here that we need to understand are characterizations of volcanoes. So one is going to be active. That means it has erupted within the last 10,000 years, and it's very likely that it could erupt again. Another is dormant, and what dormant means is that it hasn't erupted in the last 10,000 years, but there's still a chance it could. And the last is extinct, and that means that not only has it not erupted in the last 10,000 years, but it's not expected that it's going to erupt anymore. So it's basically sleeping and never getting up. So again, when we look at these different types of things, we need to understand that they all come from the Earth. The Earth provides all of the energy required for these processes, and that energy can come from the inside or closer to the outside. One last tidbit is that when the energy comes from the further inside, it's less dangerous because it has to travel further to get out. That's what we call a deep focus. When that energy has to travel less far and it's closer to the surface, that's what we call a shallow focus. That's the start of that energy, of that breaking of that crust. So the focus is where things start inside the Earth. The epicenter is where they start on the surface of the Earth. And all of those things combined, the starting of the energy, the spreading of the energy, is what leads to both earthquakes and volcanoes.